Um, right, so the magnetic field of a planet, in fact, is already the first mystery because you know about magnetic rocks, which have a magnetic field. But we know now that if you have a rock with a temperature above the Curie temperature, it loses its magnetization. And we know that the interior of Earth is very strong, is very hot. So it shouldn't be magnetized rocks which generate Earth's magnetic field. We also know that the magnetic field of Earth is slightly variable in time, which shouldn't be if it was just magnetized rocks. And it turns out that the magnetic field of Earth is generated by currents and what we call the magnetic dynamo. So you need a conducting material which is in motion. So it's moving. You have a small seed magnetic field which is amplified. And I'll spare you all the details, but this is roughly the idea how we get a magnetic field on Earth. And if we zoom in a little bit on this motion, because this motion is really important, it can have two different reasons. We can have what we call thermal convection, where we have a liquid zone, and this liquid zone needs a thermal gradient. So in Earth, we have this liquid outer core, which is very hot at the center and much cooler outside. And then these hot inner part wants to get out, so it moves up because it has a lower density. So this thermal gradient drives this kind of convection, and that's something that works for terrestrial planets, as we have seen, and it also works for giant planets. So the giant planet is hotter in the interior, cooler at the outside, because that's where it's cooling. And if we go back to the terrestrial case, there's one very important ingredient, that's the mantle, right? Because the Earth does not stop at the upper boundary of this liquid core. Above you have the mantle, and then you have the crust. And if these are good thermal conductors, then the heat can be conducted out in an efficient way. So the top layer of this core is cooling, and this is what drives the convection. And in some cases, for some planets, you may have a very bad conduction in this mantle, so that the heat is just storing up. It can't be extracted. And in that case, the temperature gradient from bottom to top is very low, and convection breaks down. So in those cases, it will be much more difficult to drive a magnetic field. And that's the case, for example, when you have a planet without plate tectonics. That's what geologists, geophysicists call the stagnant lid configuration. You have a lid which is closing the heat and it cannot get out. All right, so that was, let's say, the first mechanism. And there's a second one, which we call compositional convection, where, again, you have a liquid zone. But in addition, we need a solid zone. So for Earth, we have a solid core in the center, which is mostly iron. You have the liquid zone just above it, where you have a mixture of iron and sulfur. And when this mixture freezes out at this boundary layer, it freezes out in a different composition than what is in the mixture. So it would like to freeze out only the iron. It is enriched in sulfur, and then this sulfur wants to get up. And again, this gives a chemical gradient which drives convection. And that, in fact, is very efficient in the sense that a typical terrestrial planet, in the beginning, it will have a liquid core where you can have thermal convection. Things work nicely. Then at some point, you can form a solid inner core, right? You cool it enough that something can solidify in the center. So then you have both thermal convection and compositional convection. And if you continue cooling for years and years and billions of years, then everything is solid. Well, when everything is solid, convection breaks down. So that's a quick summary of these two modes. We have thermal convection, which works in terrestrial planets, mostly in the initial phase. And all the time for gaseous planets. And then we have the compositional convection, which works only for terrestrial planets, but that's what drives the magnetic field on the long term. Just to give you one example from the solar system, if we look at Venus, according to satellite measurements, we have a liquid core, but we do not have a dynamo, right? There's no real magnetic field intrinsically. And yeah, and it's not totally clear why, but one possible reason is that the temperature gradient between top and bottom is too small because Venus does not have plate tectonics. So the crust of Venus is pretty much the same since many, many millions of years, and then we think the heat cannot go out. And this maybe also apparently has prevented the formation of a solid core, and then yeah, you don't have compositional convection. So if you look at this track, that's a kind of sketch, an estimate. For Venus, you had thermal convection in the beginning. You had a magnetic field, but as it cooled down, this field dwindled, and Venus was never able to switch on the second, more important mode, which is compositional convection. So it does not have a magnetic field. And for Earth, it was probably the same in the beginning. So we had thermal convection, a magnetic field, which was strong because everything was hot in the beginning. The field decreased, and at some point, compositional convection started. That's when the solid inner core formed, and then the magnetic field jumped up and kept more or less constant. So that's the picture that we use. And now we'd like to know how this picture can be transferred to planets outside the solar system. A few words on this. And here we use slightly different variables, but it's always the same idea. So you need convection. And if you look at hot Jupiters, at gaseous planets, you need something hot, which in this case is more easily expressed as the luminosity, because that's an observable quantity. So the planet from the beginning, it has its residual heat, which makes it still observable today. And as this planet cools down, the luminosity decreases, which means that the energy available for this convection will go down. And most likely, if you look at the lowest curve on this diagram, lowest curve is Jupiter, you had a strong magnetic field in the beginning, and then it decreased because the planet cooled and convection decreased as well. So in some sense, the picture for gaseous planets is relatively simple. You just need a few parameters. You need its age, you need its luminosity, and you can estimate its magnetic field. It will not be precise, but it's, let's say, the potential magnetic field it could have. For Earth-like planets, and especially for super-Earths, which are more massive than Earth, it's more complicated. It's more complicated in the sense that you really need the structure of the planet because, as we said, we have this mantle, we have this heat, and we have to get this heat out of the interior of the planet, and that depends on a lot of ugly details. Let me just show you, I think, 3 examples. So if we look at the case of Earth, we said in the beginning we have thermal convection, which is slowly decreasing, inner core forms, and you get compositional convection, which is much stronger. That's the main mode, which then sustains the magnetic field of the planet. But there's a number of extra variables which we have to take into account if we want to be sure we understand it. So because the cooling process is also strongly defined by how much heat can get out from the planetary surface. It will depend on the surface temperature. You see that if you change the surface temperature of the planet, the magnetic field estimation changes a lot. And then we've also mentioned the case where you do not have plate tectonics, where the heat gets locked into the planet and cannot get out. That's the difference between the upper curves. PT means we do have plate tectonics, and SL means we don't. So that's the stagnant lid configuration, no magnetic field. You may form a solid inner core, but it happens much, much later, right? So For this Earth-like planet, it would happen after 6 billion years, and the field comes very late. And then it depends on the mass of the planet. As the planet is more massive, it takes more time to get rid of its initial heat and to be able to form this solid inner core. So if you're at a 3 Earth mass planet, the magnetic field may take 6 billion years or longer before it can be formed. And that's just examples. There's other little problems that can happen when you have Earth-like planets. So the main message for this is for gaseous planets, you can kind of estimate a magnetic field. For Earth-like ones, you really need detailed models. All right, after this introduction about magnetic fields on these planets, I'd like to explain why we think they are important. They're important for a number of reasons which really go through the whole history of the planet. The planet formation, the planetary migration, when it is formed, where does it stay, does it change its orbit? It's important for the planetary atmosphere, which can get lost if you have a lot of stellar wind or CMEs, which can rip off part of the atmosphere unless it is shielded by a strong magnetic field. You can also imagine cosmic rays, which come from the galaxy, which could go to the planetary surface unless you protect it. And then there's a number of observables which are modified if you have a magnetic field. Let's just look at a few of those in a bit more details. So I've picked the example of cosmic rays because that's the one I probably spend most time on. So if you have cosmic rays coming from the galaxy, from supernovae, from wherever they are coming, acceleration regions, they come to the environment of the solar system, the heliosphere, or if you think about exoplanets, we'd call it the astrosphere, which is a kind of magnetic layer which will shield away parts of the particles, but most would get to the top of the planetary magnetosphere. The planetary magnetosphere, depending on the magnetic field strength, will shield a number of planets of particles. And then you have another layer, which is the atmosphere, which can shield the planet again. And those which cross through all of these layers will get to the surface, and then they can interact with the surface, they can interact with biological systems at the surface. So that was the aim of this study. And we looked at the spectrum of galactic cosmic rays outside of the magnetosphere. So you have high numbers of low energy particles, and as you go higher in energy, the number of particles decreases. That's related to the acceleration process. And then if you switch on the magnetic field, the number of particles that get through decreases, particularly at the low energies. So that's the idea. And we differentiate between cosmic rays from the galaxy, which have the spectrum I just showed, and cosmic rays which come from the star, which have a slightly different spectrum, which are created much closer to the planet itself. So for this study, we took a dozen of energy bins. We took cosmic ray particles, protons of different energy ranges, which we started outside the magnetosphere, and then we followed the trajectories. Let me show this again, of the particles going in. Particle goes in, some of them are reflected, some of them really get to the surface. We followed the trajectories of a few 100 million particles, and then we counted how many particles reach the top of the atmosphere, and especially at what regions. You see that, as it should be, the equator is well shielded, and most particles that get in at the poles. And with this I try to summarize the result. So if you have very high energy particles, of course, they get through. Your planet is not shielded, even with a very strong magnetic field, but those particles are very rare. When you have lower energies, parts of the particles are deflected, another part gets in. And then you have a And when you get to low energies, then most of the particles are reflected, deflected, they cannot get in. They are either shielded by the magnetic field, or they get through the magnetic field, but then they have to go through the atmosphere. And this is just the case of 1 times the Earth's magnetic field. So in this case, m is the magnetic field strength, it's not the mass. If you go to a weakly magnetized planet, you see that, and it's not really surprising, the proportion of particles that get through is increasing a lot. Right. So what do these particles do? They arrive in the atmosphere. They interact mostly with the ozone layer. So they destroy ozone, and part of that gets removed, which means you get a higher ultraviolet flux at the surface. And they also create secondary particles, especially muons, and these muons reach the surface. And in the end, the effect was not as strong as I expected, because if you go to a very weak magnetic field, you just lose 15% of your ozone layer. That's not that much. You get 30% more UV. Okay. And you increase the muon flux by a factor of 2, but you could increase it by a factor of 10 if you don't have the atmosphere. So for this, it seems the atmosphere is a much more important ingredient in the planetary shielding than the magnetic field. So that was the case for the galactic cosmic rays. For stellar cosmic rays, it's a little bit different. So the increase of ultraviolet is not just the 30%. You can increase your ultraviolet radiation by a factor of 40, which is still reasonable, right? If you want to take vacation on one of these planets, you need a sun blocker with a factor of 40, which will then protect you. What was more interesting is we found that in the atmosphere, these cosmic rays, stellar cosmic rays, modified some of the chemistry, and especially created a lot of hydrogen nitrous oxide, HNO3. And this means that if you look at these planets and you have a reasonably good resolution in a spectrum, you could locate these the quantities of these molecules, and then maybe use it as a diagnostic to see if this is happening on the planets. So maybe that could serve as, tracing how much stellar particles arrive and what the magnetic field is looking like. So that's the summary of the effects of cosmic rays, galactic cosmic rays and stellar cosmic rays. So indeed, the muons are mostly shielded by the atmosphere, and in the solar case, the same is true for the ultraviolet radiation. The most noticeable effect is that will slightly change the spectrum that is observed. That's what specialists call biomarkers, and they search for these different molecules. Another effect of a planetary magnetic field is the erosion of the atmosphere of the planet. So you have to realize that if you look at a young star, it has a much higher X-ray and ultraviolet flux than the star has at a later age. And this high flux of X-ray and ultraviolet photons will extend its atmosphere. So really the atmosphere of some of these planets can be very, very large, which means it can interact with the stellar wind or stellar coronal mass ejections in a much more efficient way, especially if you don't have a magnetic field. And in those cases, the atmosphere can be removed. That's something that we try to roughly estimate with very simple models a bit more than 15 years ago. So if you look at the habitable zone, in around M stars, so the smaller stars, the habitable zone is much closer to the star, which sounds good. But then if you're closer to the star, you get much more impacts by coronal mass ejections, and you might get this strong stellar wind, which both of them together can remove an important part of your atmosphere. That's something that you have to think about when you model your planets, when you think about planetary evolution. So that's, let's say, the beginning of these models. And of course, nowadays there's much more sophisticated models based, for example, on MHD simulations, where basically the idea is the same. You have strong stellar wind flow, or you have CMEs which arrive, which compress the magnetosphere. And if then the magnetic field is too close, then the atmosphere can get removed. So it's nice to see that this, let's say, this kind of work is still ongoing. Now let's look at a few observational tests. I said magnetic fields are important. How can we know whether they exist? One of the earliest tracers that was suggested was the chromospheric emission of a star. So in this case, we're looking at the interaction of the planet to the star. And what was suggested is that as the planet passes, this magnetic connection creates a kind of hotspot at the planetary surface. And this hotspot would lead to an enhancement in our calcium 2K line, which seemed to increase periodically, right? This is where it came from. There were these observations, and people tried to understand where they were coming from. And indeed, it could be star-planet interaction. But unfortunately, it is not necessarily a proof of a planetary magnetic field, because it was shown a little bit later that this star-planet interaction can happen even if the planet is not magnetized, right? So this interaction is important, and it needs a stellar magnetic field, but not necessarily one on the planet. And that's a much more recent study which goes along the same line for the planet HIP 67522b, where the number of flares seems to increase in a specific geometric setup. And that's really just the stellar magnetic field, which is not perfectly symmetric, which sweeps over the planet and which then creates these extra flares. So indeed, the stellar magnetic field is important. Planetary magnetic field, we don't know. So this is just one example. I had a few other ones, but I removed them in the end. The important message is that most methods that have been suggested to measure a planetary magnetic field indirectly have what we call false positives. So there's a second effect, or more than one effect, which can create the same signature, and you cannot use them to prove magnetic field is present on the planet. Right, we just had a look at the, where is it? Star-planet interaction case, but there's many others. There's one exception to this, which is radio emission. Because radio emission from the planet would be linked to charged particles moving in the magnetic field lines. It's something that we know, for example, at Jupiter. It also happens at Earth, but it's more difficult to observe for the terrestrial emission. It's something that happens at low frequency through what we call the cyclotron maser. And in fact, the emission frequency is directly linked to the magnetic field at the location where it happens. The rest is just natural constants, right? You have electron mass, electron charge. And here it's easy. If you have this emission going on, you measure your frequency, you know the magnetic field. Or if you have a planet where you switch off the magnetic field, you will not have this emission. So this emission is really a very good tracer in the sense there is no false positive. It's difficult to measure, but if it's there, it's there. Now, there has been a lot of work on the details of this radio mission. I'm not going to go all of these theoretical studies, which all looked at different small or major effects. Of course, there have not only been theoretical studies, there also have been observations. The earliest observation, I find that quite funny, was in 1977, which is much, much earlier than, even the discovery of exosolar planets. So they tried to observe radio emission from exosolar planets before knowing where these planets were. Just assuming we know stars should have planets, let's try to do that. So, of course, this is work that has been ongoing now for quite some time. We don't, or none of these teams does have a detection at the moment, but the theoretical predictions seem to say that we're pretty close to the detection limits, and that's what motivates people to continue the observations. So just a few of the observations that have been tried. Some of them are tentative detections. Maybe there's something here, but in the end, maybe it was a background source. Maybe there's a small decrease in the flux, but statistically not very significant. So it's really a very difficult business because with just one observation, you are never really sure of what you see. And one of the planets that was studied the most is one called Tau Bootis b, and Tau Bootis is a double star, so we call it Tau Bootis capital A, B, so first planet around the first star. And each of these little dots is a previous observation that has been done. And if you compare to the theoretical prediction, which is this orange line, well, it should be in principle detectable, but you have to observe it at the right moment with the right telescope. And that's what we tried as well, because this is really one of the most favorable ones. And that's what we saw in 2017. So we had a signature at a frequency of about 20 to 30 megahertz. So we're really happy. That's a tentative detection we made with LOFAR, with Jake Turner and Philippe Zarka and a few other people. But of course, we immediately had to think about what the signal is. So first of all, it's a very weak signal, right? It was a 3.2 sigma detection, so it is probably real, but we are not 100% sure. And even if the signal is there, where is it coming from? Is it really coming from the planet? Is it maybe coming from the star? Does the star just have a random flare when we observe it? We cannot really rule it out. Can it be star-planet interaction creating emission at the star, or is it emission at the planet? So we did have circular polarization, which is a strong argument for the planet. But this being an extraordinary claim, we really thought we need extraordinary evidence, and just one signal like this was not enough. So we tried to observe again to increase the significance, to get a better hold on this detection, and also to search for something periodic, to see if we have a signal which is repeating periodically with maybe the orbital period, which would point at a planet as the origin, or maybe a periodicity with the stellar rotation, which would hint at emission at the star. And in fact, we expect neither one nor the other. We expect the beat period, but for that, of course, you need several detections first. So we set up a follow-up campaign for which we used LOFAR, the LWA, UTR2 in Ukraine, and Nenufar, which was just built in Nançay at that time, just finished construction. And we decided to improve the phase coverage because the old observations from 2017, we just had a few measurements, but we didn't cover the full orbit. So with the new observations, we tried to cover the orbit as well as possible. We reobserved in 2020, and we didn't see anything. So that was a big disappointment, just showing you how frustrating it can be sometimes. But you didn't want to give up at that stage. So we had to think how could it be that we have a signal in 2017 and no signal in 2020? Of course, the original detection could have been a false positive. It's always possible, especially with a 3 sigma detection. It's an option. We could have a problem with the cyclotron maser condition, which is not always fulfilled. That's a bit technical, but this radio emission at a planet needs particular conditions, and if the atmosphere is evaporating, it could temporarily block that emission. Maybe the magnetosphere was depleted, no particles which could emit, or maybe just the emission is variable. And indeed, we realized that the star around which this planet orbits has a magnetic cycle. So it is rotating, of course, and it has a magnetic cycle which is relatively short. It's 120 days. And if you look at it, just the rotation of the star could change the magnetic field encountered by the planet by about an order of magnitude. So maybe if we were observing at the wrong moment, the interaction was much weaker. And I mentioned the magnetic cycle of the star. So if you look at the same star a couple of months later, the magnetic configuration is changed. And if you look at the magnitude of, if you compare the scales of these diagrams, even the maximum emission that could happen in June 2008 was lower by a factor of 4 than in January. So what we really need to know is the stellar magnetic field at the moment where we observe in radio. Because then, if we do not detect the planet, we know whether it is because of the stellar magnetic field. And if we do detect it, we can more easily interpret the detection. And indeed, having the stellar magnetic field is possible. It's possible through what is called Zeeman Doppler imaging. So that's where the optical telescopes come in. They observe the star regularly, and from that they can construct magnetic maps. So we decided to set up a new campaign in 2023, where we observed with Nénuphar for the radio and one of the optical telescopes on Pic du Midi to get a magnetic map and then compare and make this correlation. And for the first time in my life, I had observations which were killed by bad weather. I'm a radio astronomer, I don't care about clouds. But in fact, yeah, for the magnetic maps, I need them. I need optical data. I didn't get them. No magnetic maps. We don't know. So we set up a fourth campaign, 2024, with LOFAR and Nénuphar for the radio, with Pic du Midi and a Canada-French-Hawaii telescope for the magnetic map. The observations happened, so we do have magnetic maps. We have the radio observations. They are partially processed. They're not finished, so that's something I'll show you next time I come here, I hope. And I'll continue working on this next week. So we have a big team because we need people to analyze the radio data, the optical data, to extrapolate the optical measurements to the location of the planet. It's a lot of work, but I really hope we'll be able to know more about these planets. Fingers crossed. And then, of course, for the little bit more distant future, we'll have LOFAR 2.0. So we already mentioned this XLO collaboration. So when LOFAR 2 will be operational, probably 2026, we'll observe many planets, including this one. And we also are setting up collaboration with the optical colleagues to make sure we profit of the lesson we have learned. We do need magnetic maps. And then we'll have SKA. So SKA will search for this kind of emission in the group which is called the cradle of life. So that's observations for, let's say, 2030, maybe a bit later. SKA is construction is going on, but there's some slight delay. And maybe there's crazy plans, or maybe not so crazy plans, for observations from the moon. I didn't dare to put a decade, but I think this would be a very nice complement to these observations. So just to summarize, because I covered a lot of different subjects, I started with planetary magnetic fields to mention there's two different mechanisms which can create the magnetic fields. It's always convection, but it can be driven by a thermal gradient or a compositional gradient. And we looked at how these two mechanisms could work at extrasolar planets. We've seen that these planets could have a magnetic field, maybe not all of them, but many. Especially for the terrestrial planets, it depends on the detailed structure. You really have to check a lot of details. Now, of course, magnetic fields are important. They define how the planets evolve. They are there during all their life, from their formation, how they keep the atmosphere, how cosmic rays get to them, etc. Then we had a look at observational tests. There's many that have been suggested in the literature, but most of them have false positives, which makes it complicated, except for radio observations. Radio observations are going on, and fingers crossed that we find something. Thank you very much.
Thanks a lot, Jean-Mathias, for this very nice talk, and it was very clear.
You.
Difficult to give a talk in so many different topics, but you
Yeah.
did very well. So we have plenty of time for questions. Maybe if we, okay.
Thank you so much for a nice talk. Very nice summary of very different topics, as Miguel says. Going back to tau routines, yeah, you mentioned that you want to go back to the same phase of the cycle, of the magnetic cycle of the star, in which you had your first detection. And you are trying to do that with spectropolarimetry from some of the imaging from these images. A cheaper way would be just to look at the light curve of the star in the long term. If you have a very clear periodicity of this magnetic cycle in the photogrammetry, you could go just to the same phase, but a number of cycles later, and try to do the observation there, and you make that likely and find you can do emission.
Right. So indeed, the ideal thing would be to go back to the phase in the magnetic cycle where we had our first detection. I'm not sure this is really possible because, I mean, there is a number of magnetic maps of these stars. We see the cyclic variation, but imagine if you look at the Earth with the 11 or 22-year cycle, if you go back in time, you will never have the exact match. So I think the idea is it's easier to describe it as we want to know what the magnetic field looks like when we observe. So we observe, when we get observing time, when tau Bootis is nicely observable during night. Nighttime observations are better. And get a magnetic map at the same moment. So if we have a detection, we can understand it in the light of the magnetic field. And if we get a non-detection, we can also better interpret it. But I don't think it's reasonable to target a very specific phase in the magnetic cycle. It's probably not regular enough. But you're right, we could look at stellar light curves to already know which maybe some years are more interesting than others. But yeah, 120 days is pretty short, so.
Sure, depends on how precise your periodicity is. You can go farther in time to try to get to the same phase. If you have large errors in the period, probably you won't match the phase a few years later, because this is a very short period, that's for sure.
Yeah.
We we did the opposite. We went with what I am telling you. We went to a star. We detected some star-planet interaction, and this star has an 8-year magnetic cycle. We went to the same phase a number of years later, and we actually detected.
Okay.
Again,
I'll look into this. I think 118 days is a bit short for this, but it's definitely worth having a look. Thank you.
Thanks, Taylor, for the question. Tim?
Thanks for that. Very grateful. I'm curious, did you look if you could make the spectrum maps or just those IMAP in all the low-power archival data that's within 1 or even 2 degrees of Tau-Bootes? Because the large field of view can give you unexpected discoveries. And it may be that you had convenient coverage, probably not, but it could be worth investigating.
So for these observations, the radio observations, I don't think we had imaging data. We had used LOFAR as a beamformed instrument pointed to Tau-Bootes. We had a few extra beams around it to correlate and compare and have good statistics. And indeed, if we had imaging data from the same time, that could be used in that way, using this DIN-SPEC-MS method.
Thing is at least covered once from the surveys.
Yeah.
And it may be that there are targeted observations from the dedicated projects which happen to be nearby.
Okay, I can look again in the LOFAR archive. Yeah, it's a good idea.
Go ahead, yeah.
Talk a bit more about how doing these observations from the moon would be helpful. Just curious about that.
Ah, yes. So the moon is nice because on Earth we have the ionosphere, and the terrestrial ionosphere blocks all observations below 10 megahertz, and even between 10 and 20, it depends a lot on local conditions. Sometimes it's okay, sometimes it's bad. And if you go to the moon, you could observe to much lower frequencies. And it's a bit far away, but the radio emission of a planet is linked to its magnetic. The frequency at which it emits is linked to the magnetic field. So if you can go lower frequencies for observations from the moon, for example, you could study planets with weaker magnetic fields. So that's the idea. Of course, the problem is for LOFAR we have 100,000 antennas, and for NENUFAR we have 2,000, well, 1,824 to be precise. But it's not enough to put one dipole on the moon. That's enough for tests and initial phases. But what we really need, if you want to search for a planet, you need at least 1,000 antennas. Otherwise, you won't see anything.
Need to become a friend of Elon Musk.
That's a good plan.
Awesome.
Yeah.
More questions to Jean-Mathias? I have a question at least. So, Jean-Mathias, could you clarify a bit the expected magnetic field of the planet Tau AB? Because, of course, as you show here, this formula is really linked, and you had this tentative detection around between 20 and 30 megahertz. So, based on that, you could work out the magnetic field. But how did you approach initially why Tau would seem to be such a good target? Could you comment on that?
Right. So for the radio observations, the big challenge is that you want more than one observation. You want to cover, maybe I had it earlier. No, you want to cover the full orbit, and covering a full orbit is expensive in observing time, right? If you have an orbit of even 2 days in this case, you need a number of observing sessions. The observing sessions can be maybe 4 hours, but then the planet gets too low. So you can't do that for millions of planets unless you piggyback on imaging observations, which is true. In this case, you can do a bit more. But you have to very carefully select your targets, especially when you do beamformed observations. And indeed, Tau-Bootes fulfills many of the very simple criteria. So you want a source which is close to the solar system. If you have a planet which is far away, its emission will be very weak. It's a planet which is close to its star, so the interaction with the star is supposed to be strong according to all of these theoretical estimations. And it's a relatively massive planet, probably around 4 times the mass of Jupiter, which gives it a stronger magnetic field. And again, that improves the interaction. So if you look at all of these criteria, it was one of the best planets, and that's why we focused a lot of effort on this one. It's not the only one we studied in this amount of detail, but as soon as we got this first tentative detection, of course, we focused on this one for follow-up.
So, questions, Matthias?
Thank you for the talk. It was very clear. I just have one question. In the beginning of the talk, when you were talking about the differences that you find between the galactic cosmic rays and the stellar cosmic rays, are these differences because of the number of cosmic rays that you have, because of the density of these cosmic rays, because of the chemical composition? Why did you find these differences?
Right. So in both cases, the galactic and the solar cosmic rays are dominated by protons. So I only looked at protons. I did not look at any other chemical species. It's about their energy spectrum, which is related to their acceleration mechanism. And it's this one. So galactic cosmic rays have a lot of particles around 1 gigaelectron volts, and the solar cosmic rays, they're accelerated in the sun, which is a bit less violent. So there are much more particles, but because we're closer to the source, but they are lower energy. And I didn't put it on this one, but if you'd add the solar spectrum, it would be higher, but more to the left. So that's the main difference.
Yes, it's a really very nice talk, particularly for the non-expert people. I'm working on the Earth atmosphere, and I'm curious about why HNO3 could be a proxy of is it the stellar cosmic rays, or?
Yes. Yeah, that's pretty indirect. So you have the cosmic rays coming in. I have it somewhere. Yes. So the particles come in, and actually they do not directly destroy ozone. They ionize, they create secondary electrons at the top of the atmosphere. And that leads indirectly to the creation of nitrous oxides. And these nitrous oxides, they have a catalytic cycle which destroys ozone. That's why they're particularly evil, because each can destroy an ozone, and then it's regenerated and it destroys another ozone molecule. And in this big chemical network, I think it's the nitrous oxides which also create this HNO3. I have to look again at the chemical reactions, but it's not totally direct.
First, maybe one final question. Was the last one was?
Yeah. So thanks for the very comprehensive talk for our specials. I have a curiosity. Now is very, very nice question. You were showing the very beginning, the introduction, the magnetic field for super Earth. So I'm wondering if it's not necessarily the intensity of the magnetic field is not necessarily related to the mass, right? Because yeah, exactly, that's right. Because massive planets they do not necessarily have a stronger magnetic field, right? It depends on other factors.
Yes. So for this, the idea is that if your planet is more massive, and if the composition is the same, so there's already a lot of assumptions, but you have a bigger volume of this liquid core, which then stays hotter longer time. And you have to cool it, you have to remove its heat before you can form the solid inner core. But for that, you have to go through a very thick mantle. And if the planet is more massive, the mantle is thicker as well. So it takes more time before that starts. That's why the 2 Earth mass planet starts this chemical convection much later than the 1 Earth mass planet. And if your planet is too big, it maybe, according to this model at least, never happen. And I'm not saying this model is perfect, right? It probably has been improved since, but Sometimes people say super Earth are much better than Earth. Let's look at life at super Earth. There's good arguments, but there's also arguments which say you have to be careful. Maybe super Earth planets have a problem getting a magnetic field. Thank you.
Just on this, does this apply only to Earth-like, I mean, sorry, rocky planets, or this is also?
No, that's rocky planets.
Rocky planets.
Gaseous planets are different.
Super Earth, okay.
Yeah, indeed.
Okay.
Also, regarding this same topic, what is the effect of the rotation of the planet, the speed of the rotation? Is taking into account is a constant value assumed or?
Yeah, so that's a difficult question, actually. In the beginning, I thought it's very straightforward. I didn't put a slide on this. But in the beginning, people suggested that the rotation drives the magnetic field. But if you look at dynamo simulations, for them, they come to a different conclusion. They say you need a minimum amount of rotation, probably to break the symmetry, so you can have something, some global field emerging. But then whether it rotates at this minimum speed or 10 times more, it doesn't change that much. And according to these simulations, once you have this minimum amount of rotation, the decisive quantity is how much energy you have. And the energy is, in that case, not linked to rotation anymore. So it kind of depends on which approach you are taking. And I don't think we really know the answer yet.
Okay, so there are no more questions. Let's thank Jean-Mathias for this great talk. Before we leave, we are going to Donde Siempre to have lunch. So if anyone wants to join, please let me know. So I booked a table, but you know, we are maybe too many. We need to book. Martin?